Our previous lesson established a geometric breakthrough. We can represent the relative phase variable as a physical coordinate on a sphere. In this framework, the phase variable, theta, is treated as a concrete physical property rather than an abstract numerical value. We explicitly mapped theta as the azimuthal angle along the equator of this mathematical sphere. By embedding the phase on this equator, we lock the variable into a continuous, unbroken circular space. Now that phase exists as a geometric circle, we must determine the mathematical rules that naturally govern its behavior. The first discrete symmetry acting on this circular space is the cyclic symmetry of order 3, known as Z3. Z3 enforces a rigid mathematical constraint on the potential energy, providing a formal structure that goes beyond the casual observation of three things happening. This symmetry requires us to analyze the continuous phase circle through a framework of strict, equidistant intervals. Conceptually, the phase is transitioning from a free-flowing ring into a structurally constrained track. Establishing the baseline topography of this system requires the application of these strict Z3 constraints. Looking directly down at the phase circle, we define how Z3 operates geometrically. Z3 requires invariance under a precise 120-degree phase shift, corresponding to 2 pi over 3 radians. Repeating this shift 3 times returns the system to its starting point, creating a closed cyclic structure. Invariance means that shifting the phase by this amount must leave the entire potential energy landscape completely unchanged. If the landscape were to alter during this shift, it would fail the Z3 constraint and indicate a broken symmetry. This strict geometric repetition generates a threefold organization across the entire phase space. Consequently, any equation describing the potential energy of this system must possess this 120-degree immunity to change. We will now translate the geometric rule of Z3 invariance into a functional mathematical equation. This is the simplest non-trivial harmonic potential that satisfies the Z3 constraint. The coefficient lambda sub 3 represents a positive value in this formulation. The central component is the input of the cosine function, the factor of 3 theta. This multiplier of 3 functions as the architectural linchpin of the entire equation. The factor of 3 theta compresses the standard cosine wave, forcing it to repeat its cycle 3 times within a single 360-degree rotation. The 120-degree geometric shift and the mathematical 3 theta multiplier are now formally linked. Because of this factor, calculating the potential at theta yields the same result as calculating it at theta plus 120 degrees. The equation V sub Z3 of theta equals negative lambda sub 3 times the cosine of 3 theta stands as the lowest order harmonic potential that satisfies these symmetry requirements. To understand the physical topography created by this equation, we must find its stationary points, where the landscape flattens out. We differentiate the potential with respect to theta. Stationary points occur only where this derivative equals 0, meaning the sine of 3 theta must be 0. This condition is met at regular intervals of n pi over 3. Since stationary points include both peaks and valleys, we must specifically filter them to find the minima. In the potential equation, the deepest valleys occur when the cosine of 3 theta equals positive 1. This condition is met at the radian coordinates 0, 2 pi over 3, and 4 pi over 3. These translate directly to the geometric degree coordinates of 0, 120, and 240 degrees. Calculus confirms that the Z3 invariant potential creates 3 perfectly spaced energetic bottom points. We can now visualize the resulting landscape of the phase space by combining the geometry with the calculus. Every well in this structure is identical in depth and shape. These 3 coordinates represent the classical baseline minima of the symmetric theory. This structure represents an idealized state of perfect symmetry. This symmetric baseline provides the necessary starting point before we introduce the specific physical distortions used in later models. In those subsequent stages, the topography will face corrections such as chiral bias and coherent stiffness. We must establish this foundation before addressing those dynamical corrections. Geometric phase and Z3 invariance together mandate this uniform threefold structure. This leads to a final question. If the Z3 symmetry were broken at the start, Would the later structure still have any reason to prefer threefold organization? Our next lesson will examine how these perfect minima respond when the system